Okay, today we're going to talk about fixed point problems. Consider a problem like this, g of x equals 0. Oftentimes you can solve these by just rearranging them to make it look like a fixed point problem. You just put everything except x over onto the other side. Start with some value of x0 and iterate until you get to the desired precision. But wait, does this work? Not usually, no. Consider the following two equations. You have x prime equal f of x and x prime equal f inverse of x. If one converges, the other definitely doesn't converge because they both have the same fixed point, and they produce basically the same sequence, but one produces it in the forward order and the other one in the reverse order. So if one's converging, the other one's moving away from the fixed point. Here's an example to show this problem. We're going to do a simple quadratic, but we'll rearrange it this way. We'll try to solve it as a fixed point problem. Let's go to a spreadsheet and see what happens. Okay. Well, we'll choose the parameter a. We'll just choose 1 just to make it simple. We'll choose x0 equal to 1.5, and then the formula is a over f of x. The difference is the difference between x and f of x, which should be going to 0. And then we'll bring these down, and we'll compute the rate of convergence, which is the ratio of the differences. We'll use an if statement to avoid dividing by 0. And we'll bring those down. And the rate of convergence is -1, which is not good. We need it an absolute value less than 1. So it's not working. Let's look at a graph to see what's happening. We'll start with 1.5. And we plug 1.5 into the function f. That's like looking at just taking a vertical line and then taking the value and plugging it in again is like taking a horizontal line. And then we go up, get another value of x, we compute f of x, and we wind up basically where we started, exactly where we started. We're not getting closer to the solution. It didn't work in this case. Why not? When does it work and when does it not work? Here's an example where it works. This is just a simple straight line. The slope is gradual enough that it makes it work. If you can drive on the red line, if it's not too steep, then it's usually convergent. So we go up to the curve to the right, go up to the right, and since we started to the left of the fixed point, we're getting closer. Eventually it gets close enough that we can't really see the difference between the estimate and the fixed point. So this is a stable example. We could have started on the other side, by the way. We could have started above the fixed point. We could have started at 1.5. We'll do that example next. So here we're starting at 1.5, and we'll go down to the red curve and then to the left. So down to the left, down and to the left, and keep going until we get the desired precision. We can also find stable versions where the slope is negative. In that case, it tends to spiral around in the circle. Let's do a negative sloped version. We'll start at 0.5. So in this case, we'll start below the red line and we'll move up. Then we'll go to the right. Now we have to go down and we'll move to the left, and we kind of spiral around the fixed point. But we're getting closer. Some people call this the cobweb. Now let's look at an unstable version. What makes a version unstable? Well, if it's too steep to drive, then it's unstable. We're going to start with a value of close to the fixed point, 0.95. It's going down and to the left, which is the wrong way to go. It's moving away from the fixed point. It's blowing up. We would have had the same problem, but in the reverse if we started above the fixed point. Let's start with a value, let's say 1.05. In this case, it will go up and to the right, up and to the right. Again, that's the wrong way to go if you started off up and to the right of the fixed point. We also have a problem if the slope is downward sloping, and it's too steep to drive again. Here we'll start just a little bit below the fixed point, 0.95. Even though we're starting close, it'll soon spiral out of control. It goes up to the right, down to the left, up to the right, down to the left. But instead of getting closer to the solution, it's spiraling out of control. I have to change the fixed point problem in order to make it converge. Let's just go over what makes a stable and an unstable. There are 4 zones here. The left zone is the triangle to the left. The zone 2 is the triangle down below. Zone 3 is to the right. Zone 4 is above. Stable methods go from zone 1 to zone 3, or from zone 3 to zone 1. Unstable versions go from zone 2 to zone 4. Or from zone 4 to zone 2. Or actually from zone 2 to anything, zone 4 to anything. Well, we can modify the function to make it converge by subtracting a parameter. The 1 minus beta in the denominator is there to make sure that we get the same fixed point, but it'll have a different slope now. If you plug in f of x equal to x, you realize, oh yeah, it will be the same fixed point. Let's go to a spreadsheet, try putting in this parameter beta and seeing if it helps converge. So we're just going to modify the example to put in a parameter beta. We'll start out with beta equal to 0, but we can adjust that later. So we subtract a beta x in the numerator, and then we have to put a 1 minus beta in the denominator that makes sure that we get the same fixed point. So with that little adjustment, let's bring it down and see what happens. Obviously nothing happens until we choose beta equal to something other than 0. 0.1, oh, that didn't work. Let's try it the other way. Minus 0.5, oh, that worked. It's getting closer. Choose a different parameter a. Oh, okay, now that works. Okay. Can we combine two adjustment parameters? Yes. There's a fairly simple way of adjusting them. When you do the math, just plug it in there. You realize it's equivalent to a new parameter tau, where tau is the sum of the two parameters minus the product. Went through that kind of quickly, I understand, but you can try working it out on your own. So let's go back to the spreadsheet and put in tau and see if we can adjust our problem in steps. So we'll just copy all this over. We'll create new parameters gamma and tau. Tau will be the sum of the parameters minus the product. And all we do here is make the parameter tau the instead of beta. And we'll bring that down and we'll try a new value. Oh, okay, now it converged much more quickly. This is like the Babylonian method. Okay, let's try another example. And once you understand this process, you can invent a million different examples. This is a quadratic example. And sure, we could solve it using square roots, but we'll do it this way. We'll just put everything over to one side, make it a fixed point problem, and solve for it. Does it work? It works for small values of a. So let's create this example. Choose a small value of a. Let's choose, let's say, 0.01, 0.1. Okay. The fixed point is close to 0.5 times A. So let's modify the formula. It's minus 0.5 times A, and then minus 1/2 x squared. Once we typed in the formula, we'll bring it down. See how well it converges. It does converge. And I can guess what the beta should be. It seems to be 0.4888. And then choose beta, though, equal to minus x0, because that's a little simpler for right now. We can improve it with gamma. Okay. Notice tau is about minus the fixed point. Okay, when we choose A to be a smaller value, we don't need a value of gamma. It converges very rapidly, as fast as Newton's method. Now when we choose a big value of A, like 1, it's a little bit more problematic. We are able to get it to converge, but it's harder. In an A of 9, it really takes some work to make it work. All right, let's think about another example that we could do. How about changing the example to be a quintic? Same kind of idea. Solve for x. When A is small, this will work. Easy to modify the example. Let's just copy this example over and put it into a new spreadsheet. I'll change the parameter to something smaller. And then change the formula. It's 0.2 times A, and then minus 2x squared minus 2x cubed minus x to the fourth minus 0.2 times x to the fifth. Have to make sure you type in all of that correctly, or you won't get anything useful. Oh, by the way, I can see something. I need to change the x0 value. It should be 0.2 times A. And beta looks like it should be about minus 4 times x0. Yeah, that converges really well. You can play around with different examples. You can try different formulas and see if you can get it to work. This fixed point method is really simple for finding solutions of problems. Thank you.